Section 3.2, combining probabilities with and or. Goals here, be able to find and probabilities, be able to find the or probabilities, and be able to find probabilities with two-way tables. So what we're going to see is that the words and or lead us to two different ways of combining probabilities. And the first one we'll focus on are and probabilities. So and probabilities are used to find the probability of two or more events occurring together. So for example, if you flip a coin and then roll a die, you might want to find the probability of obtaining heads on the coin and then a 5 on the die. So let's take a look at a tree diagram for this so we can start to build up the formula concept behind these and situations where you want to see more events occurring together. So we'll start out here. I'll have the coin, and when I flip a coin, I have two outcomes possible. I've got the head or the tail. And then for the actual die, I've got 6 outcomes possible. And off the tail, if I flip tails, I can still have 6 possible outcomes for the die. So we've got the die outcomes 1 through 6 here, and we have the die outcomes again if we did tails here. So what we have to keep in mind, if I'm looking for the probability of a heads on the coin and a 5 on the die, that's really going to bring me down this path here to right here. So I have heads, then a 5. And if we look at the total number of outcomes, always counting across the bottom of the tree, when I draw the tree in this way, we've got 12 total outcomes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that head with the 5 is one of the 12 possible outcomes. So the probability then of getting heads on the coin, 5 on the die would be 1/12. So let's see how we can get that using some actual numbers of probabilities and lead up to like a formula of some sort that we can actually use. So the coin, heads was a 1/2 probability, tails was a 1/2. The die, you got a 1/6 probability of each of these little branches occurring. So 1/6, 1/6, all the way across here, 1/6. I'm writing them small, but they're all 1/6. Maybe I should give myself more room. So 1/6, 1/6, all the way across here, 1/6. So I know that the heads then a 5 was 1/12. And one thing to note is that 1/2 times 1/6 is 1/12. So one way to think of this is the probability of head and 5 would be the probability of heads times the probability of 5, which is going to be equal to 1/2 times 1/6, which equals that 1/12. So this basic idea of being able to multiply the probabilities in the and situation works in special cases, and this is one of those cases. And let's talk about this a little bit more. What's so special about what we just saw here? And basically what we saw here is that flipping the coin and rolling a die, they don't affect each other. When you flip the coin, it's not going to change your outcome of what you got on a die. There's no interrelation there between the two events. So if the two or more events have happened, each event does not affect the others. So, the flipping of the coin doesn't change what's going to happen when you do something with the die. And in general, the one event happening doesn't have any effect on what happens in the other event. Then you can just multiply the individual probabilities together to get the overall probability. So there's a special name for this idea when one thing doesn't affect the other, and it's called independence. So two events are independent events if the occurrence of one event has no effect on the probability of the occurrence of the other event. So basically, like I just said, one thing isn't affecting the other. And in order to use this following rule, this and probability rule, the events must be independent. We're going to see an and show up later on, but the events won't be independent, so we'll have to handle it differently. But for this one, we can just do that. And sorry, I want to move that down a little. So if events A and B are independent, that's crucial, then the probability of A and B is just the probability of A times the probability of B. It's just multiplication. And again, I can't stress this enough. This is when the two events are independent. They don't affect each other. So example 1, you roll one die and draw one card. What is the probability you get a 2 and a heart? Well, the probability of 2 and a heart would just be equal to the probability of a 2 times the probability of a heart, because rolling the die is going to affect what's happening when you draw the card. So you're going to get 1/6 from the 2. There's 1 2 on a die. And then in a deck of cards, remember we talked about this before, there are 13 hearts out of the 52 cards. So when you multiply, you can look, or multiply fractions I should say, you can look and see if things reduce. So the 13 over 52 does become 1/4. This makes it a little easier, especially if you're doing it by hand, and you get 1 over 24. So the next one here, you flip one coin, roll one die. What's the probability you get a tails and a 4? So similar to what we saw up above. Probability of tails and the 4. This is going to be equal to just the probability of tails times the probability of 4, because the tails, the coin, is independent from what's happening on the die. And we'll get here just 1/2 times 1/6, and we get the 1/12, just like we did up above. So again, ask yourself, are these events independent? If they are, then you can just multiply their probabilities together. And that's the idea with the and probabilities for independent events. Okay, or probabilities. These deal with situations where you are okay with more than one outcome. So for example, if you roll a die and want to know the probability of seeing a 1 or a 3, it's 1 or a 3. I don't care which one comes up there, I'm going to be happy. So let's look at the die sample space for this. So we have the 1, the 2, the 3, the 4, the 5, and the 6 being our set of possible outcomes. And if I want to know the probability of a 1 or a 3, well, I'm going to circle that 1. That would be good. I'd be happy with that. Or a 3. I'd be happy with that. So looking at this, we can see that there are 2 numbers out of the 6 that satisfy my desired event, my outcomes of 1, outcomes of 3, both make me happy. So 2 out of the 6 will be the probability of a 1 or a 3 occurring when you roll a die one time. So 2 out of 6, reduce that down to 1/3. Now one thing to note here that's going to be important for building up the or probability formula is that if you take 1/6 and add it to a 6, then why am I picking 1/6? Well, the probability of 1 on its own, just rolling a 1, would be 1 out of 6. The probability of rolling a 3 alone on its own would be 1 out of 6. But notice what happens here when you take those individual probabilities and add them together, you get 2 out of 6, or 1/3. You get the same thing as what we saw when we used the sample space approach. And we are going to try and build up to a formula that allows us to avoid writing out the sample space. So in this case, we can just add the individual probabilities. But there is a but, so to speak, with this. You just add them, but there might be something that stops us from being able to do this just adding them together without any other adjustment. And we'll talk about that here right now. So the key to being able to just add the individual probabilities is the concept of mutually exclusive. Two events are mutually exclusive if they have no outcomes in common. And when I look up here and I see the 1 or the 3, well, when I circled the 1, that was the only thing, the only outcome that was a 1. And when I looked at the 3, that was the only thing that was a 3. There wasn't any overlap between outcomes. There wasn't something that was both a 1 and a 3 at the same time, a common outcome that satisfied both being a 1 and a 3. So that mutually exclusive idea is when you have that, where the outcomes, there's none in common between the two events. So an example of two events that are not mutually exclusive on a die roll would be odd and 3. So if you look at the sample space again, 1, 2, 3, 4, 5, and 6, and then if I go ahead and circle the odds and then put a diamond around the 3, notice that I actually have, well, diamond, I call it a triangle actually, sorry about that. So looking at this, you can, the more important thing is that the 3 outcome was common to both the odd and 3 events. So 3 is common to both odd and 3 events. And this is kind of a problem here, because if I just added the probabilities for the odd, which would be 3 out of 6, and the probability for 3, which is 1 out of 6, I would get 4 out of 6 as the probability. Well, looking at the total number of things that have been circled or put triangles around, there's really only 3 of them. So by counting that 3 twice, essentially, once as an odd, once as a 3, I've distorted the probability when I just add those together. So in this case, you have to undo the fact that the outcome 3 got counted twice, once as a 3 and another time as odd. And to undo this double counting, you must subtract the probability of the common outcomes. Just undo it by subtraction. So the addition rule then says, if A and B are any events, then the probability of A or B occurring is going to be probability A plus probability of B, and then minus the probability of A and B. And this is the probability of the common outcomes. So in that example above, the 3 showed up as both odd and a 3. So there's 1 out of the 6 that's both an odd and a 3. So we'd be subtracting away 1 out of 6 to undo that double counting. And if A and B are mutually exclusive, which means they have no common outcomes, that common outcome probability is 0, you can just add the 2 probabilities together like I did in the first example and not worry about subtracting. So I'm going to stop here. We'll see you in part 2.